Okay, so today's topic is polynomials. First, though, let's review one of the problems from last time that I wanted to cover, but there was not enough time. Yeah, so this problem is the following. You have a 5 by 7 checkerboard, and you want to cover it by L's, but it's a little bit different from these standard tiling problems. You want to cover it by L's in such a way that the L's can overlap, but it needs to be an equal covering. Okay, so it's a little bit different. Um, okay, and the question is, can you do it? Can you not do it? And the solution that I want to present is okay. It's tricky to come up with. So the idea is you need to consider this coloring here. So it's a coloring in 4 colors. And it's okay. So what is the property of this coloring? It's the property is that if I look at any square, okay, so
Can
it
have all
doesn't.
four numbers.
Exactly right. So the point of this coloring is every square or 2 by 2 square has each number exactly once. Okay. But you know, our tiling is not by squares, it's by L's. But when we use L's, it still has the property that any L, doesn't matter how you orient it, is gonna have distinct numbers. So it'll have 3 out of the 4 numbers exactly once. Okay. And now how do we understand whether or not? Okay, I'll spoil the problem. The answer is you cannot do an equal covering by L's. And what's the reason? So so why is it not possible? The okay, here's the main thing. You you need to understand, you know, how many ones are in the board. So I pick one because it's the most frequent color. If you count how many ones, so okay, so there's total of
We
35.
have one more one and more ones and more threes as well.
Um, yeah, so what's the number? So for ones, let's count. So for I think there's actually the most one. One occurs the most, even more than three, I think, right? Because
In this
so let's
example, yeah, I thought we were talking about the 5 by 7.
yeah, so for 5 by 7, what happens? So I have okay, so 5 by 7, it ends
It
here.
ends in with 1 and 3, so you
Right.
always have like
So one, three, one,
extra ones
three,
and threes.
one, one, two, three, four, five. I think you'll have the most ones, right? Because the all the corners are ones, right?
Oh yeah, you saw 2 1. Yeah, that's funny.
So yeah, so what is it? And it means okay, how many ones? So there's going to be 3 times 4 ones, right? So 12 ones. There's 3 times 4. Um, that makes sense. Yeah, it's like it's here, 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 here. Um, okay, and what's the point? This number is more than 1/3. Okay, 1/3 is 12 over 36, and this is more than that. So more than 1/3 is one, but that should not be possible, right? Because if I'm doing an equal covering, well, okay, first of all, okay, if I do an equal covering, I'll get this proportion of ones, but each L is at most 1/3 the color one. Does it make sense?
Mm-hmm.
Like each L, either it has, 1 out of the 3 tiles is one, or it has none of them. Either way, the proportion of ones is at most 1/3. And so we have a contradiction. Okay. So does it make sense? Any questions about this? The, okay, so I wanted to present this. It's kind of, I don't know. It's kind of,
Could you explain the contradiction again?
yeah, so the contradiction is I want to think, okay, I cover this with L's, right? And then, so for each L, I'm gonna, so okay, let's say I did like this. Let's say I put an L here, okay? And now I keep track how many of each color there are. So when I put the L here, I get 1, 4, 1, 2, and 1, 1. If I put another L, let's say I put another L like this. So remember, they're allowed to overlap. Now I get a 1. Well, it's the same colors, okay? But if I can now maybe I can put another L here. Okay, I get 1, 3, and 4. Okay, so I'm just tallying how many of each color there are. And at the end, I'll have covered the board. I'll have equally, like, there'll be overlaps, but I'll have equally covered the board. So I know
All
at
right.
the end, the proportion will have to be exactly the proportion of the squares. So at the very end, I know there's going to have to be 12 out of 35 proportion 1 in this tally. Does that make sense?
Yeah, and then at most, okay, no, continue.
Yeah, so now what's the at most 1/3? Well, in this tally, whenever I put down an L, I'm adding 3 numbers to the total. I'm adding 3 tallies to the total, but I'm increasing 1 by at most 1.
Okay, yeah, I get it. Okay, thanks.
So it's at most 1/3, but yeah. So that's the contradiction. It's very so you see it's like very specific to 5 and 7 being small numbers. Like if 5 and 7, if I take a huge board like 100 by 100 or something, then it'll be roughly equal proportion of each color. This argument doesn't work.
I see.
So it's very specific, right? Do you see why it's like very specific to be a small number? Yeah, it's kind of I don't know. They call this Russian combinatorics.
Russian?
Yeah, I mean, it's a Russian problem, and like the competition is the Russian Math Olympiad, and this style of combinatorics where you do something clever and who knows where it comes from. It's called Russian combinatorics. Okay.
But why can't we generalize to bigger numbers?
So let's take a
We
bigger
should-
number. Yeah, go ahead.
I was saying like we should be able to just like be more of an issue of figuring out which numbers appears more than others.
So let's take a big number. Let's take something like 55 times 77. Okay. Now the point is, now I can say, okay, I can take which number, I can color it again, and 1 will appear the most again. But the problem is the proportion of 1 will now be very close to 1/4. Like it's not going to be 12 over
Right.
35. Yeah, you see now, right? And 1/4 is not more than 1/3, so it doesn't work anymore. It's something very specific about 5 and 7 being very small. Okay. So it's you can ask, if I take a bigger board, is it possible? And I don't know the answer to that, so it's something you can think about. Okay. All right. So any questions before we move on to the main topic for today? Okay. So, right. So today's topic is polynomials. So I want to start with this problem, which is one of the warm-ups. So yeah, the first couple of problems, the theme I want to emphasize is divisibility and roots. So roots of a polynomial tell you something about divisibility, right? If I have r as a root, then x minus r divides the polynomial. So yeah, it's a very simple idea, but it's very powerful. So let's see how we can use it. So the first problem, it says, suppose p of x is a polynomial of degree n that satisfies p of k equals k over k plus 1 when k is 0, 1, 2, ... n. Okay. And you want to ask, what is p of n plus 1? Okay. So any ideas where we can start? So, you might be tempted to say p of n plus 1 equals what? N plus 1 over n plus 2, but it turns out that's not correct. That's not the answer. But yeah, so any ideas where we can start?
We know that 0 is a root.
We know, yes, we know p of 0 is 0. So that tells us that, okay, 0 is a root, so it tells us x divides p of x. Okay.
Mm-hmm.
Okay, what else? So we've used, the first condition, but somehow we've been given like n plus 1 conditions, right? And which, by the way, is like you should there's some intuition here, right? Like you're given a degree n polynomial. What does that mean? It means p of x equals Cn x to the n plus Cn minus 1 x to the n minus 1 plus all the way to C0. So there's n plus 1 unknown coefficients, and you're given n plus 1 values, it's a polynomial. So you're given n plus 1 constraints. So it should uniquely determine the polynomial. Question is, what is the polynomial? So, any ideas? Okay, so let's, okay, maybe I think it's better take something a little bit easier than to begin with. So let's consider a slightly different problem, which is find all polynomials p of x of degree n such that p of k equals 1 or k equals 0, 1 through n. Okay, so it's a similar, similar setup, but I've told you that, because it's a degree n polynomial, and I've told you the values at 0 through n, but now I'm just telling you that they're all 1. Maybe it's a degree less than or equal to n, I don't know.
Isn't that just a constant polynomial?
Okay, so constant polynomial works. Is that the only polynomial that works? So yeah, so there's a proposal p of x equals 1 works.
I think we should consider the polynomial b of k minus 1
Great. So we should
because
consider.
0, 1 up to n are all roots of b minus 1. So there are n plus 1 roots of b minus 1.
Okay, great. So
And we know that I think it must be constant. It must be constant.
Yes, I think you're. So let me write down all your steps, Karan. Let me write them down. So you said, so the first thing you said, which is very important, right? So consider the polynomial p of x minus 1. Okay, so p was a polynomial of degree at most n. P of x minus 1 also a polynomial of degree at most n. And what you told us, Karam, is that this polynomial, let's give it a name actually. Let's call it q of x. Q of x has roots 0, 1 through n. Yes?
N plus 1 roots.
Yes, and so in particular, this is n plus 1 roots.
So it must be constant, because if it was not constant, it will be a contradiction, because if it's not a constant, it has at most n roots.
That's right. So yeah, so this is very important here, right? So we have a polynomial, we know it has n plus 1 roots, but we know the degree is at most n, right? So yeah, so p has degree at most n, so q has degree at most n. But as degree at most n and n plus 1 roots, it must be 0. Does it make sense to everyone? This is a very important thing, right? Like, so this is kind of what the point of the fundamental theorem of algebra is, right? Like if I have a degree n polynomial, I have n roots, right? So if it has n plus 1 roots, it must be 0. Does it make sense?
Yes.
Okay. So yeah, so what does it mean? Okay, it means that okay, a little bit out of space, so maybe I will write here. Okay. So it means, what's the idea? P of x minus 1 equals 0, which implies that P of x is the polynomial 1. Okay. Does it make sense?
Yes.
Okay. Okay, so let's do a little bit of a different example. Let's do okay, I want to do what? I want
So the original B will the same idea have the same idea.
for this for the original problem. Okay, so before we go to that one, I want to do one more similar problem. Okay, so I want to do one more. So so I'll come back to your idea, but first I want to do one other problem. So okay. Okay, so okay, so for this problem, so for the P of k equals 1, right? We found, okay, it must be identically the polynomial 1. But let's do something a little bit different. Let's say find all polynomials P of x of degree less or equal to n such that P of k equals k, or k equals 0, 1 through n. Okay.
I think maybe the same idea because
Explain, yeah.
the B of k minus k will be a polynomial of degree that is less than or equal to n.
Great. So this has degree less than or equal to n, and as before, it has roots.
N plus one root.
Yes, n plus 1 roots. Right.
So it's
there
it's
we go.
0.
There we go. So yes, P of x minus x equals 0, and P of x equals x for all x. Okay. Does it make sense?
Yes.
Okay. All right. So yeah. So okay. So now let's go back to the original problem. This one here. So how do we solve this one?
I think we should consider the polynomial k plus 1 of b of k times b of k minus k.
Great.
Yeah.
Okay. Great. So I mean, okay, great. So you said I'm going to write x. I'm going to write x instead of k because it's a polynomial, not the integer values. So you're saying we should consider the polynomial q of x, which is x plus 1 times p of x minus x. Okay.
It will be at most n plus 1 degree.
Okay, so the degree of q is at most n plus 1, so it went up by 1, right? And then what is true about this polynomial? Has these roots as before, right? So zero, 1 through n. Okay. Okay, so what does it mean? Do we conclude q of x is 0?
Q of x will be we can vector q of x is x minus 1 x times x minus 1 times x minus 2 times x minus n.
Great. Yeah, so this time we don't get that it's 0 because the
Constant.
degree is actually equal to the number of zeros. But what we can say, we can factor q of x as x minus 1, all the way to x minus n. And
or q will be a constant. We have two cases.
So okay, so I want to say, even in this case, there's something you're forgetting. It's not just, we don't know immediately that it's of this
Times a constant.
Times a constant, right? And the point is the constant can be 0. So your other case is also actually the same as this case.
Okay.
Do you see? So C can be 0. So there's actually just one case. It's just, you see?
Yes.
Yeah. Okay, good. So C can be 0. Yeah, but so, okay. So now we know a lot, actually. Other than C, we know what is Q. Okay, so what do we do from here? Actually, maybe I'll pause. Maybe let's before we can I'll pause. Does everyone understand what we did here?
Yeah, I got it.
Okay, good. Okay, so yeah. So what's the next step? What do we do now? Because we know something about Q, but remember we want to know about P, right? So
maybe x plus 1 cannot divide the q, plus x, q of x plus x.
you want to see, you're saying we want to know what C is, right? And the way you're gonna do it is you're gonna say, okay, so yeah. So now the question, right? What is C? And what you're saying, you're proposing, well, how do I determine what is C? You're saying, okay, I look here and I say, x plus 1 must divide q of x plus x, right? So let's write it down. Let's, you're saying x plus, oh, no, I will write it in maybe blue this time. So I'm looking at this expression, I'm just rewriting it a little bit. And I'm saying x plus 1 times p of x equals q of x plus x. So in particular, it means that x plus 1 divides q of x plus x. And okay, so now we can use this to figure out what is C, right? So how can we do this? Let's do this. Let's make some space. So let's take all of this, let's move it up. Okay, so what do we know? We know x plus 1 divides, let's instead of writing q of x, let's write this. So we say x plus 1 divides c times x minus 1 dot x minus n plus x. Okay. What does this mean?
And maybe we can vector x.
Okay, you can factor out x. So one thing you can do, you can write, okay, this guy here is x times c x minus 1 all the way x minus n plus 1. Okay. But okay, I want to say, okay, remember, this section is called divisibility in roots. What does it mean that x plus 1 divides this polynomial?
And minus 1 is the root of this polynomial.
Yes, that's the better way of thinking about it, right? Like minus 1 is a root, right? And that's something we can just yeah. So what does it mean? It means minus 1 is a root of c times x minus 1 x minus n plus x. But okay, then we can plug in minus 1. We can see what happens. So it tells us what c times -1 times a -1 minus 1 is a -2 all the way to
so we can find c now.
Yeah, now we can get c, right? So plus -1, it's 0, right? So this is good. Okay, so it's like this, right? So yeah, and so yeah, let's simplify it a little bit. So this is saying now what c times -1 to the n plus 1 times n plus 1 factorial, right? That's what that guy is equal to 1. Yes. So c is -1 to the n plus 1 over n plus 1 factorial. Yes. And that's right. And that's c. Okay.
Why is it to the power of n plus 1, not just n?
Okay, so what happened here? So I
We have
was
n
here.
plus 1 like factors, yeah.
So
That's
yeah,
just...
so
Oh yeah,
so
n plus 1. Oh,
yeah, you see it, yeah? I just wrote this
yeah,
guy.
my bad, my bad.
I pulled out -1 n plus 1 times, and yeah. Okay. Good. So this is our C. Now what? Now what do we do? Okay, so now it means we know what Q is, right? Because we know C and we know Q is like this, so we know Q. So let's write that. We know what Q is, and okay. Maybe I write it here in green or something. Okay, so maybe I'll use black. I don't know. Okay, so equal to -1. No, yeah, okay. -1 to the n plus 1 over n plus 1 factorial times what? Times x minus 1 all the way times x minus n. Okay, and now we're basically done, right? Because we know Q and we can use that to get P. And once we know P, we can do P of n plus 1. So let's finish the calculation. So maybe I can put a new page or something. Okay, so we know what is C. I don't need this anymore. And okay, so what is so P of x will be Q of x plus x over x plus 1. So what is it here? It's -1, the n plus 1 over n plus 1 factorial is x minus 1 all the way x minus n plus x over x plus 1. Okay. And it will tell us P of n plus 1 is, what we want is what? So when we plug in n plus 1 here, we'll get n plus 1 n all the way to 1. So we'll get n plus 1 factorial. Good. Okay, so n plus 1 factorial plus n plus 1 divided by n plus 2, which is what? So this is n plus 1 plus a sine plus or minus 1 over n plus 2. That's the answer. Okay. So it's very close to the naive guess of just n plus 1 over n plus 2, but there's a correction. Okay. Okay, so does it make sense? Any
Yes.
okay, so yeah, I think this is a very nice illustration of like what do we do when we talk about polynomials, right? We like, you know, why did I call this divisibility in roots? Because okay, sometimes like when you know something is a root, you know that x minus r divides, and when you know x minus r divides, you know it's a root. So you have to go between these two perspectives if you want to, you know, work with the polynomial. Okay. Okay. Yeah. Let's see. So any questions? Should I move on? Okay. So great. Yeah, so let's go to this problem. It's very similar. It's a P of x is a polynomial of degree n, again, that satisfies P of k equals 2 to the k. And this time, and again, for k equals 0, 1, 2 through n, and we want to know what is P of n plus 1. Okay. So basically, we want to figure out what P of x is. Like once again, you know, it's a degree n polynomial, and we're given n plus 1 values. Okay, so so any ideas what we can do here?
Maybe we consider the relation B of k plus 1 equal 2 times B of k.
Very good. Right, so this is a great. Right, we're P of k plus 1 equals 2 P of k. Great. What do we do with this?
Maybe then subtract 2 B of k. Maybe this will give us like roots, dealing with roots.
Okay, great. So yeah, let's do this. So let's look at the polynomial. I'm going to call it Q of x again, which is P of x plus 1 minus twice P of x. Okay, and so this one has roots 0, 1, all the way to n. And let's see, what is the degree? Yeah, the degree is n, right?
Most n.
At most n, yeah. In fact, yeah. So yeah, it has degree at most n. And in fact, if P is degree n. Sorry, Karan, I didn't hear.
Yes, it must n, but I'm not sure it may exactly be n.
Yeah, so I think so. Okay, I guess the problem tells us that P has degree exactly n. And I think it's enough to tell us that Q has degree exactly n, right? Because let's think what's going on. So if P is something like Cn x to the n plus Cn minus 1 x to the n minus 1 all the way C0. So what happens when we look at P of x plus 1, we get Cn x plus 1 to the n plus Cn minus 1 x plus 1 to the n minus 1 and so on. The only term that will contribute to the leading term, right? It'll come from here, right?
Yes.
So what I'm saying. So all these guys, they won't contribute to the leading terms, only here. So the leading term of P of x plus 1 is Cn x to the n. Okay. But then when I do, yes?
Isn't assuming that n is a root the same as saying that Pn plus 1 is equal to 2 to the power of n plus 1?
Oh, you're right. Yes, that's true. That's right. So it's and that's
This
in fact
finishes
okay.
like the question, like just
Yeah. So no, we actually it's in fact n is not a root. Thank you for pointing this out. This is only true up to n minus 1. Very good. Very good. Right? Because right. So let's clarify. So P of k equals through the k for k equals 0 through n, which tells us P of k plus 1 equals 2 P of k, but only for k equals 0, 1, all the way to n minus 1. It's not true for or sorry, all the way true for n minus 2.
Isn't it up to n?
No, it won't be. No, it will only be true up to n minus 1. Do you see? Because
yeah, because P of k plus 1. Okay.
yeah, if it was true for n, I would know P of n plus 1, right? So it's not
yeah,
true for so yeah. So this is very important, right? This is very important because otherwise you will get something too good, right? So it's very important. So yeah, so thank you for this comment. So this is only true up to n minus 1, so the roots are only up to n minus 1. Okay, so yeah, so let's finish the discussion on the degree. So we said P of x plus 1 has leading term Cn x to the n, and minus 2 px. Okay, we can see what it is, but the point is the leading term will be minus 2 Cn x to the n. So in total, Q of x, it will have leading term minus Cn x to the n. So actually, it'll have degree exactly n, and the leading term will be minus the leading term of P. Does it make sense?
Yes. So can vector Q of x.
Yeah, so the degree of Q is exactly n, and so we can factor it. So yeah, so we're given its degree, it has degree n, and we're given n of its roots. Okay, so we can't conclude at 0, right? So this is why it's important, Adam, that you pointed out the mistake, right? Because otherwise we would have just said, oh, there's n plus 1 roots, it must be the 0 polynomial. Okay, that's not the case. It has exactly n roots, so we know it's, we don't know it's 0, but we can factor it, right? So we can write q of x is equal to some constant times x minus 1 all the way times x minus n, okay? And for some constant c, which could be 0.
It will be
Yes?
x minus n minus 1 plus 1.
Oh, yes,
Because,
sorry. Yes, I wrote the wrong, sorry, I wrote the same thing again. X minus n plus 1. Very good. Okay.
and c is just c sub n.
That's right. Maybe minus c sub n, right? I think maybe minus.
But why minus? Oh yes.
I think minus, yes? Yeah, I think minus. So, okay. Okay, so, okay, so maybe I'll make a comment here. It's not actually obvious to me, even if I knew what Q was, like I can figure out what C is, it's not obvious to me that I can figure out what P is. You see, like this definition here, even if I know Q, I don't really know how to get back P.
But we can
But
find bn plus 1.
yes, that's very important. So yeah, I can't figure out what P is, but I can figure out what P of n plus 1 is. So I'm going to make that comment here. So even I can't get back P from Q, I can at least say P of n plus 1. So let's write it like this. I can get P of n plus 1 because what does it say? It says Q of n plus 1 is equal to C times what? Times n plus 1, n all the way to, no, I will consider Q of n. Sorry. I will consider Q of n, and Q of n will be C times n all the way to 1. So C times n factorial. Of course, by definition, what is Q of n? It'll be like this. So Q of n is P of n plus 1 minus 2P of n. Okay. So it tells us that P of n plus 1 is equal to 2P of n, which, okay, we can say, we know P of n is 2 to the n, so it's 2 to the n plus 1, rather. Maybe we can write like this. Plus C times n factorial. Okay. Does the calculation make sense? The point here is, if I want to know P of n plus 1, I just have to figure out what C is. I don't need to figure out what the whole polynomial P of x is. In fact, I'm not even sure how to do that. But I need to know what C is. Then I can do it. Okay. And by this comment here, figuring out C is equivalent to figuring out the leading term of P. Okay. Okay, so any questions so far? So now, okay, I'll admit when I put this problem on this handout, I didn't think finding C would be that hard. But then when I tried to solve it, I realized it's not so easy to get C. So okay, let's see. Does anyone have any ideas how we can get C? So
Uh,
yeah, let's see. So here's an idea. So I'll kind of explain the idea, then I'll give you some time to think about it. So let's add a duplicate check. Go here. Okay. So Okay, maybe I will erase this stuff here.
Can't we find C from either the product or the sum of roots?
So let's see. So no, because so okay, you're thinking of Vieta's formulas, right? Like you're thinking, okay, there's a coefficient I want to know, and Vieta's formulas tell me that okay, sometimes if the coefficients are related to the roots, right? So for example, let's have an aside on Vieta.
Yeah, I'm saying
Vieta,
like the sum of roots, which would be n plus 1 multiplied by n plus 2 over 2, that's equal to C over, oh, that would be C over 0, then doesn't make sense.
no, it's not C over 0. No, you have okay. So what does it mean? It means okay. So what is the sum of the roots? So R1 plus
The
all the
sum
way
of
to
roots is
Rn.
negative Cn minus 1 over Cn.
I think it's positive, right? Because the roots here are 0 through n minus 1. You're thinking here, right? The roots of this of
No,
Q.
I'm just saying the formulas ends up. Well, I don't know. It doesn't
Oh,
make sense that the formula is negative.
okay. So you're talking about okay. So is this one okay? So this is negative Cn minus 1 over Cn, right? That's the formula for the sum of the roots.
Mm-hmm.
Adam, do you know where this formula comes from?
Yeah, I can show it. It takes a bit of time. Isn't it from the fact that the sum of roots, like when you multiply them and expand them, it gives the coefficient of the second
Exactly right. It's exactly
term.
right. But you see, now the point here is, in Vieta, what do? I take this ratio. So that ratio deletes this factor of C. Do you see? Like when I do this, like whatever this ratio is, it doesn't care what C is. Like it'll like I could double the entire polynomial and this ratio won't change. So like you cannot use Vieta to figure out the
Yeah,
prefactor
got
C.
that.
And that makes sense, right? Because C has nothing to do with the roots. Like the roots is some collection of information that's related to Vieta's formula, but the C is different. It's like a completely like to give up you up to identify a polynomial, I need to tell you the roots and I need to tell you the leading term. Those are like two different pieces of information. So I shouldn't be able to use the roots to figure out the leading term. Do you see what I'm saying?
Yeah. So when exactly do we make sure that C is the same as Cn? Like, when do we know that C is equal to Cn?
What do you mean?
Like, isn't in some scenarios C is equal to Cn? Like C
So what
subscript.
do you mean by C and what do you mean by Cn? Because the way I'm writing it, C and Cn are the same thing, right?
Yeah, so why I don't get why we can. Yeah, I get the fact that like we can multiply the polynomial by like any number and we wouldn't change the ratio. But when
Uh-huh.
can we use the ratio to find C?
We can never do that, right? The point is
Never.
the point is the ratio just is it's not really like they're unrelated. Like that's why I'm saying the roots are one piece of information and the leading term is a different piece of information. They're unrelated. Okay, so
Isn't the degree of Q of X n?
yes, it's degree n.
So why does it end with x minus n plus 1?
So it has n roots, right? 0, 1 through n minus 1. Do you see?
0 n
0,
0
1, 2, all the way to n minus 1, right?
Oh, okay, yeah.
Yeah, you see it has n roots. Okay. All right. So The one way you can do this is like this. So let's do the following. So we know, okay, in terms of C, right? In terms of C, we can calculate P of n plus 1. Okay. And in fact, in terms of C, you can calculate P of n plus 2. So this is not what the problem asked for, but it's okay. We can see it's an interesting thing to do. So you can say P of n plus 2 minus 2 P of n plus 1, right, is equal to C times what? Times n plus 2, n plus 1, all the way to 2, right? Okay. Okay. And
Isn't that equal to 0?
which one?
Pn plus 2 minus 2pn plus 1.
Why would it be equal to 0?
Never mind. It's not bad. Not bad. It's not.
Right. So the ones that are equal to 0, it's, if I put in like 0 to up to n minus 1, but now I'm you see, like it's yeah, so it's not 0 anymore, right? So it's okay, but okay, let's see. So how do I want to say this? Okay. I want you to think like this. So what is this now? This is so it tells me that n plus 2. Yes?
Would not q of n plus 1 be 0? Because we have n plus 1 minus n plus 1. Or
Yeah, that's what I
not.
thought, but the n plus 1 is not between brackets, so you end up with 2
Oh,
as the
okay.
final term.
I understand what people's
Yeah.
confusion is. I should write this
Yes.
I should write it like this, right? So maybe like this will help people. Is this the confusion
Yes.
everyone's having? Okay. Okay, good. So now I think this is okay. Good. Okay, right. So now what does it mean? So now P of n plus 2, we can write it as okay, 2 P of n plus 1 plus C times n plus 2 all the way to 2, which is what? Which is okay, so now let's plug in we have a formula for P of n plus 1, so it's something like 2 to the n plus 2 plus 2c times n factorial plus c times, and I'm going to write this as n plus 2 factorial over 1 factorial. Yeah. Does it make sense? Does everyone follow this calculation? Okay. So I'm going to do one more. I'm going to do P of n plus 3.
Why do we start with n plus 2? Shouldn't be n plus 1 multiplied by n, going down to 2?
What do you mean? Here.
No, on the line above it. Oh, it's the same thing.
Here, yes, okay. So
Yeah,
here.
shouldn't this be n plus 1, then n?
Did I make a mistake? Maybe I made a mistake.
It's cx, not cx plus 1, and this is this is q n plus 1.
Yes, this is q of n plus 1. Yes, you are right. You are right.
So it should start with plus 1.
Very good. Very good. Thank you. Okay, very good. Very good. I made a mistake here. So yeah, it should go n plus 1 and then n. And then what's the last term? The last term is n plus 1.
It's 2, yeah.
Is 2. Okay, good. So, okay. Very good. Okay, so I have here n plus 1. Okay, and then, okay, what do I write? So here I have n plus 1 factorial over 1 factorial. Okay. Okay. So now what? Now let's do p of n plus 3. So p of n plus 3 is going to be, okay, maybe I'll skip some steps, but hopefully it'll be clear. So it'll be 2 p of n plus 2 plus c times what now? C times n plus 2 factorial over 2 factorial, right? I think that's right. Yeah. And so this is going to be, okay, so I take double this one, 2 to the n plus 3 plus 2 times, no, plus 4 times cn factorial plus 2c times n plus 1 factorial over 1 factorial plus c times n plus 2 factorial over 2 factorial. Yeah. Okay, does okay. Well, first of all, did I make any mistakes? Okay, I think it's okay. Okay. So yeah, so any questions so far?
But how can this help us to find C?
Yeah, so how can this help us, right? So what I want to say, and I'm going to give you guys, so I'm going to say the idea, then I'm going to give you guys some time to work it out. And then if we don't, okay, if we don't work it out, we can leave it for homework. But the idea is, okay, what is p of n plus k? Okay, so p of n plus k, you can understand it will have a term that starts 2 to the n plus k. Okay, then what?
Then it's
Then,
2 to the power of k minus 1.
that's right, the next term will be 2 to the power of k minus 1. So actually, let's pull the c out. There's all the terms will have c, so it's c times something. And you're saying it starts with 2 to the k minus 1 times n factorial, right? Is that the first term, yes?
It's similar to a Taylor expansion.
So it is, but okay, we don't know calculus. It is kind of, but it is okay. You're right. It is similar to Taylor expansion, but I don't want to use calculus to solve it. But but let's see. So I'll do 2 to the k, then I'll do 2 to the k minus 2 times n plus 2. Okay, or okay times okay. I'm going to clean up the terms a little bit because okay. Here's how I'll clean it up. Instead of writing n plus 1 factorial over 1 factorial, I will write n plus 1 choose 1, and then I'll put the n factorial next to it. Is that okay? You see how it's the same?
Yes.
Okay, and then we do 2 to the k minus 3, n plus 2 choose 2, n factorial, and okay, it goes on. It goes however many, I think it'll have k, it should have k terms, right? Okay. Now what's the point? The point is, think of k as a variable. Okay. P of so think of n as a constant and k as a variable. P of n plus k is a polynomial in k. But this is an exponential function. So you see,
Yes.
the c has to be perfectly calibrated so that, well, first of all, c has to be negative. Otherwise, it grows way too fast. And it'll have to be negative, and it'll have to be calibrated in a way that it cancels the exponential part of this. Like this thing as a function of k will be exponential. This will also be exponential as a function of k. And they need to cancel, so the result is a polynomial in k. And that will help you determine c. Does it make sense at a high level what I'm saying? Yeah. This n is a constant, k is a variable. This is a polynomial in K. But the right-hand side doesn't look like a polynomial in K. This is exponential, and these all look exponential. So the C has to be chosen so that the result is actually a polynomial. It doesn't grow very fast. Does it make sense what I'm saying?
Yeah.
Okay, maybe I'll read one more thing and then let's see. Let's see. I have to duplicate this. So okay, let's do this. And then yeah, I just want to focus on the last line, so I'll delete everything before that. So okay, maybe I'll just keep it. Okay. I take this and I go here and I say, let's okay. Let's write it a little bit better. 2 to the n plus k plus c, and I'll pull out the n factorial. So n factorial times c, and actually I'll also pull out the 2 to the k. Okay. And what does it mean now? We have yeah, I'll pull out 2 to the k minus 1. That's better. So I'll have n choose sorry, n choose 0. Let's write n choose n plus 1/2 n plus 1 choose n. So instead of writing n plus choose 1 choose n plus 1 choose 1, I wrote n plus 1 choose n. And plus 1/4 n plus 2 choose 2 plus 1/8. Okay, and I think we see where this is going. And the last term should be, okay, there should be 1/2 to the k minus 1, n plus k minus 1, choose n. Yeah, so this is what I wrote here. Okay. Like this. So okay, does it make sense what I did here? It's just some manipulations where okay, I made all the binomials over n. I pulled out the n factorial and I pulled out the powers of 2. Okay.
Well, why did we make them all n over n?
Okay, yeah. So why did I make it over n? I could have not done that, but I could have not done that. It's because there's an identity. Yes, Karam, do you have an idea?
Because then the identity that says n choose k equal n choose n minus k.
No, yeah, so that's the identity I used. But I think Adam's question is why did I use it, right? Is that your question?
Oh yeah, because n over k is equal to okay, it's the same thing.
Oh, okay, yeah. So the reason it works is because of this identity, right? But okay, there's a deeper thing as why I did it, and I'll explain in a little bit. But okay, but what's the point here? So the point here is like so we think of this as a function of k where n is fixed. Then what's happening here? What's the coefficient of 2 to the k? So you see, here I get 2 to the n, and here I get n factorial times c times 1/2 times this guy. Now, the thing about this expression here, this is a, okay, it's a finite sum, But the point is the infinite sum, it converges. There's an identity, right? So maybe I'll write the identity and then you'll understand what I'm saying. So okay, what am I trying to do? So I'm saying this sum here, if you made it infinite instead, so if you said, okay, n choose n plus 1/2, instead of 1/2, let's write x, right? So, or maybe I'll t or something. N choose n plus t times n plus 1 choose n plus t squared n plus 2 choose n. I can go to infinity now, right? There's an idea that this is 1 over 1 minus t to the power of n plus 1. Is that right? The power of n plus 1. Okay. So the point is the only way this thing can be a polynomial is if, you know, this coefficient and this coefficient, they cancel.
But why is it an identity?
So now you're asking why. So you're asking me where this identity came from, right?
Yes.
Yes. Okay. So I had planned to teach this identity later, but it's good we covered it now. This is a very important, well, I don't know, it's kind of important identity. So let's have an aside where I explain what this identity is. Okay, so okay, so let's rotate the page. Okay, and so this question is about, so the identity is something like this. N choose n, t to the 0 plus n plus 1 choose n, t to the 1 plus n plus 2 choose n, t to the 2 plus t, yes, like this. So what is this? So first let's do some easy case. So n equals 0. That's the identity t to the 0 plus t to the 1 plus t squared plus dot dot dot. Okay. That's 1 over 1 minus t. Okay. N equals 1. So n equals 1, I'm saying what? Now I'm saying t to the 0 plus 2t to the 1 plus 3t squared plus 4t cubed plus dot dot dot. And my claim is that it's 1 over 1 minus t squared. Does anyone understand why this is true?
I think we at first do it for finite sequence, and maybe it like has we can split this geometric progression into some other geometric progressions, or the same progression, but the starting term will vary each time.
Yes, that's right. So what we do, we say this is equal to t to the 0 plus t to the 1 plus t squared plus so on. Okay. And then I add t to the 1 plus t squared plus and so on. Then I add t squared and like this. Okay.
Yes.
Right. So this is 1 over 1 minus t. This is t over 1 minus t. And this is t squared over 1 minus t. Okay, and so I add them all together and I'll get, the total sum will be, okay, I'll get 2 geometric progressions. Okay, does it make sense?
Yes.
Okay, so that's the first 2 cases. Okay, so what about the next one?
Maybe we can use induction.
Yeah, so you can use induction. Let's just do the next one. We'll see. So
Because the case n equal 1 depends on the case n equal 0.
Yes, you're right. So let's try n equals 2. And okay. You can use induction and yeah, so we're doing 2 to the 0. But okay, so n equals 2 will be 2 choose 2 t to the 0 plus 3 choose 2 to the 1 plus 4 choose 2 t squared and so on, right? So and you're right, it's kind of by induction. The point is, what are these choose 2? The choose 2 are the triangular numbers, right? So what does it mean? It means like this one is just 1 times t to the 0. But this one is 1 plus 2 times t to the 1. Okay, and this guy is 1 plus 2 plus 3 times t squared. Does it make sense? So, right, so what's the whole thing? The whole thing is 1 times t to the 0 plus t to the 1 plus and so on, plus 2 times t to the 1 plus t squared and so on, plus 3 times t squared plus t cubed and so on. Okay, and what is this? Okay, so this is 1 over 1 minus t plus 2t over 1 minus t plus 3t squared over 1 minus t. And if you add vertically, okay, you'll understand the whole thing ends up being what? 1 over 1 minus t cubed. Okay. Okay. Does it make sense for the n equals 2, the argument I gave? I was a little bit...
Yes, I think maybe you can do it differently, but I'm not sure.
You can do it what?
Differently.
Oh, there's another approach you have. Okay, what's the other approach?
Maybe we can say that it's equal to t is up t to the 0 plus t to the 1 plus to infinity plus 2 2t to the 1 plus or no, I mean 2 to the power of 0 plus 2 2 times 2 to the power of 1, like in the case of n plus 1.
Uh-huh.
Maybe then we can say the plus the second sum will be 2 to the 1 plus 2 times t squared plus 3 times t cubed plus up to infinity, and the third sum will be 2 squared plus 2 times 2 cubed plus 3 times 2 t to the 4 plus up to infinity. Like the first sum, the starting term will be 2 to 0. It will be like it depends at first at the case n equal 1, and then we add all the sums. Maybe we can use the case n equal 0. So I think it will work.
Okay. Okay, let's do this. So I think this identity is a little bit more involved than I thought. So let's do this. I will give it as homework for you guys to think about. How do you prove this identity? Okay, because I think it's maybe not actually that easy to give an explanation. And if you think about it for homework and you decide you thought about it enough and you want to know why it's true, you can message me. I'll give either some reading, or we can talk about it some other, maybe next class or something. Okay, but I think actually it will take a lot of time if I explain more about this identity. But for now, okay, we can just say, okay, it's true that this is true. Okay, so it's a generalization of this geometric series type identity. Okay. Okay, so now, okay, let's see. Okay, so let's do this. You can use this idea. So, you can use this idea to calculate what is this sum if you make it infinite, and then you can use that to calculate C. Okay. Just because these two coefficients will have to cancel. But I think, okay, if we continue with this method, okay, it'll take some time. So I'll say, how about this? You can do it as a homework problem. What I want to show is there's actually, I think, an easier way that uses an idea called interpolation. So, okay, so before I move on, does there any questions about like this approach here? It can work, but okay, it's a little bit messy and you have to, do some steps. But yeah, so are there any questions about this approach before I go on to I think there's an easier approach. Okay, so yeah, so what is the point? Let's just remind ourselves, right? So we know there's this Q, and we know that, okay, we know P of n plus 1 in terms of C. So in order to determine P of n plus 1, we just need to determine C. And to determine C, well, we notice it's enough. Well, what is C? C is the negative of the leading term of P of x. So we just need to know the leading term of P of x. Okay. So if we can find the leading term of P of x, we can solve the problem. And what I'm going to tell you now is actually there's a formula for P of x. So anytime I have a situation like this, where I give you a polynomial and I prescribe some of its values, like in this case, I'm telling you its values at 0, 1 through n, you can actually, there's a formula for the polynomial. It's not always a good formula, but there is a formula. Okay, and in this case, you can use it to find the leading term. So this idea, it's called polynomial interpolation. Okay, so okay, so maybe before we say what the general thing is, I'm saying if I tell you, P of x has degree n, and I tell you P of 0 equals, say, a0, P of 1 equals a1, all the way to P of say it's n minus 1, or yes, n minus 1 equals a n minus 1. So you can actually use this to just give a formula for P of x. Okay, so there will be a formula. It'll be a complicated formula, so it's not always useful, but in this case, it'll be good enough to figure out the leading term. So do people understand
Is
what?
it
Yes?
Lagrange formula?
Yeah, it's Lagrange. Yeah, so this is called Lagrange interpolation. So maybe I'll write it down. This formula is called Lagrange interpolation. Okay, but I want to explain where it comes from. Like, usually if you go to Wikipedia and you search Lagrange interpolation, it just gives you a formula, and I don't know where it comes from. But what I want to explain is actually it's a very simple formula. It doesn't. You could figure it out if you forgot about it, like on let's say 2 months from now you forgot the formula. You can rederive it. So how does it work? So I want to find the polynomial that at value 0, 1 through n minus 1 has these values. So let's do something easier. The easier thing, let's instead of completely general a0 through a minus 1, let's say we want the polynomial which p of 0 is 1, and then all the rest, p of 1 is 0, all the way to p of n minus 1 is 0. Okay? I just want this polynomial. Okay? What is it going to be? The polynomial where p of 0 is 1, and the rest, p of 1 through p n minus 1 are 0, and it has degree at most n.
It will be divisible by x minus 1, x minus 2, up to x minus n plus 1.
Great, right. So it tells us that this polynomial, let's, I don't know what to call it. Let's call it Q0. No, I don't like Q. We've been using Q a lot. Let's use it, let's call it capital A sub 0. Okay? So what I wrote the subscript 0 to mean that I prescribed the value at 0, and the rest of them have to be vanishing. Okay? So right, so Karam, you explained that this polynomial, it should be divisible. Sorry, let me just change something. Yeah, sorry, before we go there, I want to, sorry, I didn't explain this. I should prescribe, okay. The polynomial has degree n, so I should prescribe n plus 1 values. You guys understand? Because if a polynomial has degree n, remember it's cn x to the n plus all the way c1x plus c0, right? So there's n plus 1 free parameters, so I should prescribe n plus 1 different values. Okay, otherwise it won't be unique. So yeah, so I want to get p of 0 through p of n. Okay, so now I'm saying a0, it should be divisible by x minus 1, x minus 2, all the way through x minus n. So it'll be that times some constant. But can you tell me what the constant is?
It will be 1.
Well, if you make the constant
No,
1,
yeah, it will be 1 over um, 1 over minus 1 times, it will be minus 1 to the n over n factorial.
okay, great. It'll be
Because
so let me say it this way, Karam.
we want a sub 0 of 0, we want it to be 1.
Exactly right. So it'll be the unique constant, so that a sub 0 of 0 equals 1. Okay, so what does it mean? It means that c times 0 minus 1 times 0 minus 2 all the way 0 minus n is equal to 1. Okay. So right, so c is 1 over 0 minus 1 times all the way 0 minus 2 all the way to 0 minus n. Okay. So let's write it like this. Let's write it as x minus 1, x minus 2 all the way to x minus n divided by 0 minus 1, 0 minus 2, 0 minus n. Okay. So you can simplify it, but I don't want to actually. I want to leave it like this. Okay. This is the polynomial that its value at 0 is 1, and its value at the other numbers is 0. Okay, and it has degree at most n. Does it make sense?
Yes.
It will,
So now, okay, we can do it for the other one. So now, okay, let's see. Let's say I want to give you the polynomial that it will be 0 at p of 0, but then it'll be 1 here and then 0 everywhere else. Does it make sense? So it's a different polynomial. I'll call it a1 of x. a1 of x should be value 1 at 1, and then all the other n numbers, it'll have value 0. Okay. What should this polynomial be?
We can do the same thing.
It's the same thing, right? So it'll have roots x, x minus 2, x minus 3, all the way to x minus n, right? So it'll have and then so it'll have all the roots except for 1. And we can get c the same way, right? We want p of 1 to be 1, so the c should be like this. It should be x minus 2, x minus 3, all the way to x minus n, and then on the bottom we should put 1 1 minus 2. Okay, maybe I can really, what is this x? This x is x minus 0. Okay, so x minus 0. And on the bottom I'll put 1 minus 0, 1 minus 2, 1 minus 3, all the way to 1 minus n. Okay, and that's a1 of x, right? Okay. So do you guys see the pattern? Like, okay, in this way I have a0, a1, all the way to an. And now what should be p of x? Right? So if I wanted to get a0, a1, an, okay, I do a trick. I say p of x is a0 times capital A, a1, capital A1, all the way to little a and capital A and x. And that's the formula. Does it make sense? Yeah. Okay. Yeah, so I guess I will leave the general form as homework, but it's really the same thing. I mean, there was nothing special about 0, 1 through n. I mean, you could have put anything here. Yeah, but it's okay. So do you think you understand it well enough to do the general version?
How did we get p of x equal to that expression at the end?
Right. So how do we do this, right? So let's plug in let's plug in 0. Okay, let's do p of 0. So when you do p of 0, all the terms except for the first one will vanish.
Yeah, because 0, yeah.
Yeah, and here it'll be exactly a0. Do you see?
So a0 times, so this is p of x, basically.
Yeah, exactly. This is p of x. Yeah, because when I plug in I, where I is one of these numbers, only
Right.
The ith term will contribute anything. And we know what it'll contribute. It'll contribute exactly AI.
Oh, right, because it's 1.
Because it's 1,
that...
exactly. Yeah.
Yeah, okay.
You see? That's what these denominators are for. Does it make sense?
Yes.
And now you see how I can do it with any, I mean, there was nothing special about 0, 1, n, right? I could have done it with the z1 through zn. You see, as long as they're distinct. Does it make sense?
Yeah, it's just going to be a more complicated form.
Yeah, just instead of x minus 1, x minus 2, you'll have x minus z1, x minus whatever like this. Okay. Yeah, so I'll leave it as homework. Maybe one thing I didn't cover is that the polynomial is unique. Like there's no other one, but you can think about why, but it'll be unique. And it's unique because I give it it's a degree n polynomial. If I give you n plus 1, if I prescribe n plus 1 points, you should know what the polynomial is. Because that's how many free coefficients there are.
Maybe because we have n plus 1 equations with n plus 1 variables.
Yes,
So
that's the idea.
So the solution will be a unique tuple, n plus 1 tuple.
Yeah, so now maybe I'll make one comment, which is it's not always true that if I have n plus 1 equations and n plus 1 unknowns that you'll get a unique solution. It's usually true. So, but okay, let me give you a rigorous argument, Carl. So a rigorous argument is, let's say I had 2 polynomials that satisfies this. The p and p prime, they both satisfy these conditions. Then p minus p prime has n plus 1 roots. So it must be 0 because the degree is at most n. Does it make sense?
Yes.
Yeah. So that's a uniqueness argument. Okay. Yeah. So yeah. So I'll say this. I think you can do it for homework, and you can submit it as one of your submissions next week. Just write out the solution to this problem rigorously. Okay. So that includes the construction and the uniqueness. I think it's a good problem. Okay, but so going back to this problem, maybe it's here, right? You can use it here. You can use this polynomial interpolation formula. You'll get a formula for P of X. It'll be I don't think it'll be hard to understand, but at the very least, you'll be able to get the leading term out of it. And once you have the leading term, you can figure out what C is. Okay, so I'll leave it as homework, but does it make sense, the method? You can use polynomial interpolation to help you with this.
Could you go over it again?
So okay, this is an example of polynomial interpolation, like interpolation, right? I'm telling you the values, right? I'm telling you P of K, where K equals 0 through N. So you can use polynomial interpolation or Lagrange interpolation to write a formula for P of X. Now, what I'm saying is I don't know if that formula will be very helpful to figure out P of N plus 1. It'll be very complicated, but you can use that formula to figure out the leading term, Cn, right? Like P of X is equal to Cn x to the n plus all the way to C0. I think from that formula you can figure out C sub n, which means you can figure out C. Does it make
Okay.
sense?
Yes.
Okay. Yeah. Okay. Okay. So any questions on this one? Okay. So I hope this explanation of polynomial interpolation is one where you can always remember what it is, because it's not a very useful formula if you have to look it up every time. But I hope this explanation was one where, if you're on an exam and you realize, okay, I think interpolation is useful, you can figure it out yourself, right? Okay. Okay, so what do we have next? Oh, right, so the same problem. Okay. Yeah, so okay, I'll move on now. Let's see. Let me actually just look and see what I have time for. So okay. Okay, maybe we'll do this one quickly. So this is a problem. Show that x squared plus x plus 1 divides x to the fourth plus x squared plus x plus 1. Okay, so there's something called polynomial long division, and you can do long division, and okay, that's one way to do this. But I want to ask, is there another maybe conceptual reason why does this polynomial? Well, okay, yeah, like why is it true?
I remember seeing some formula about that has to do with number theory. So 4, 2, and 0 are a full set of residual classes modulo 3. So x to the power of 2 plus x to the power of x plus 1 is a divisor of x to the power. But I didn't find any proof.
I see. Okay, so let's explain this solution. So your solution is this, actually. I didn't think of this, but it's a good one. So you're
Can
saying,
we?
Karim, do you have a comment? Karim, I can't hear you. Do you have a comment? Okay, yeah, okay, so let's see. So You guys can still hear me, right?
Yeah.
Okay. So, okay, let me just, okay, so your comment was if I look at 2, 1, and 0, this is x to the 0. So the mod 3, this is a complete set of residues. And the same is true for 4, 2, and 1. 4, 2, and 0 again. Right? So I wrote the exponents mod 3. Okay. So what does that have to do with anything? The point is this. If I look at x to the
Sorry,
fourth,
but my power ran out while I was speaking.
oh, I see. Okay, did you want to explain again, or should I continue?
Can we prove it with primitive roots of unity?
Yeah, we can. So that's so we'll go there in a moment. But I did actually want to point out this comment you made, which I thought was kind of interesting. So, okay, so what this is really telling us is if you look at the difference, okay, so that the square and the square cancel, the 1 and the 1 cancel, and now here's this whole residue business, right? We have x to the fourth minus x, and so that's really we're looking at, there's the 1 here and the 4 here, and they're the same residue class. What it tells us is that this is divisible by x cubed minus 1. Okay, and x squared plus x plus 1 divides x cubed minus 1. Okay, so that's one reason. So okay. Anyways, so I think, Karim, that's kind of one way to understand the comment you made. But okay, let's see. So what I wanted to point out about this problem is when I say this divides this, one way to check is to say that, okay, are all the roots of this polynomial also roots of this polynomial? Okay. And actually, in both cases, we know the roots. They're very nice. Yeah, so what are they? So for the first one, I want to say, what are the roots of x squared plus x plus 1? So we start with this identity, right? So x squared plus x plus 1, it's a geometric series, so it has a form x cubed minus 1 over x minus 1. Okay. Okay. Now, what does it mean? It means the roots of x squared plus x plus 1, to understand them, we should really start by understanding the roots of this. But the roots of this are the third roots of unity. Okay, so we can draw them. They will be where? So the third roots of unity, they will have what? They will have magnitude 1 and argument like 2 pi over 3 and 4 pi over 3. So as in they'll be on the unit circle, because so not a good drawing. Okay, so right, so they'll be on the unit circle. They have magnitude 1, and the angles will be like, these will be 3 equal angles: 120 degrees, 120 degrees, 120 degrees. Okay, so those are the roots of x cubed minus 1. And so what does it tell us? What are the roots of x squared plus x plus 1? Well, I just forget this root, 1. So the roots of this guy are this and this, which we call the primitive third roots of unity. Does it make sense?
Yes.
Okay. Primitive third roots of unity. Okay. So now, okay, we understand the roots of this, and we want to talk about divisibility, so we need to understand the roots of this. Okay. What are the roots of this? Well, we call this guy by p of x, and the other guy is p of x squared. So what are its roots going to be? Well, P of x squared equals 0, then x squared is a root of P of x. So it's the square roots of the roots of P of x. Does it make sense? I'm saying the roots of this polynomial are the square roots of the roots of this polynomial. Okay.
Yeah.
Okay. So how do we calculate square roots in the complex plane? Well, what does it mean? So square root means, well, we think about how complex multiplication works, right? The magnitudes will multiply and the arguments will add. So if we take square root, we need to square root the argument. In this case, it's 1, so it stays 1. And we need to half the angle. Okay? But what does it mean to half the angle? There are actually two ways to half an angle, right? So this is 120 degrees. So one of the square roots will be here at 60 degrees. And the other one will be diametrically opposite here, right? Because both of them are halves, right? Like when you take an angle and you half it, you have the angle and the angle plus 180. Does it make sense?
Yeah.
Right?
Yeah.
So like if this is R1, this is like square root of R1 and the other square root of R1. Okay. And similarly, if this guy is R2, okay, so that's it's at 240 degrees, so the square root will be at 120 degrees. So it's here. And the other one is here. Okay. And so you see, two of the square roots are the same as R1 and R2. Does it make sense?
Yes.
It's because of the way the angles work. So it means that this one divides this one. Okay. Yeah, so does it make sense? Does the argument make sense?
Yes.
Okay. So I think it's a very nice problem. And I've included on the homework a generalization of this. So the problem on the homework is this problem here, which is I consider this geometric series type this geometric series type thing, x then minus 1 plus x then minus 2 all the way to plus 1. So in particular, this is x then minus 1 over x minus 1, right? And the question is, for which k does p of x divide p of x to the k? Okay. Okay, and I think the solution is kind of similar. So yeah, so I'll leave it for homework. But I hope the method is, you can kind of see, right? Okay. Okay, so any questions about this? Okay, so I don't have much time. So what I'll do is, okay, I want to do another one of these, but I'll just write it out. You can do it for homework, I guess. I didn't. Yeah, so I didn't put this on the worksheet. So okay, whatever. But you can show that this polynomial x to the 4 plus 4, it actually factors like into integer polynomials. I mean, of course it factors, every polynomial factors, but it factors into integer polynomials. Two of them, two quadratic integer polynomials. And
Isn't
okay.
that I forgot the name, cyclopolynomial, like cyclotomic polynomial?
So there is something called cyclotonic polynomials, which is very related
Isn't that how we factor x4 to plus 4? Or
No,
similar to it?
okay, so let me say something about cyclotonic polynomials. So let me finish this, then I'll say something about cyclotonic polynomials, because it's not exactly, it's almost related, but not quite. So I'll say that this is true, and okay. There's a famous identity which I've seen show up exactly once in an Olympiad problem, so I guess I can say it. It's that if you write this thing, I mean, it's related, okay, anyways. It factors like this. I'm forgetting how to factor actually. Yes. I think it's like this. Yes. Okay. And this is called Sophie Germain's identity. Okay. But if you ever wondered where did this come from, maybe you've seen it, maybe you haven't. It comes from understanding how to factor this, which comes from understanding its roots, complex roots. Okay. But yeah, that can be homework. Okay, and then Adham, you had a comment about cyclotomic polynomials, so let me sort of say something about that. It's very
Yeah,
related,
it's the thing below. It's like x to the power of the prime minus 1 over x minus 1 is equal to p of x.
yeah, okay, let me give some context. So where do these cyclotomic polynomials come from? They come from, okay, so this problem we had this, okay, we had this guy, right? You can ask what is the division when I divide, right? What is this factor? And so we can see it, the factor will have roots here and here. So there's a couple ways you can think about this. One is the roots are the negatives of the roots of p of x. Okay? So because of that, it must be p of negative x. Okay? Because the roots have become the negatives. So this one came here and this one came here. Okay? So in particular, it's this. Okay. And the other way to think is that what are these guys? What are these roots? These leftover roots in the quotient? They are the primitive sixth roots of unity. Okay. All right. Does that make sense? What I just said?
Yes.
So now, what is a cyclotomic polynomial? It comes from understanding, how do I factor x to the n minus 1? Okay, like, this problem here was something like this. Like I had, okay, like, what is this guy? It's x cubed minus 1. Okay, sorry. Over x minus 1. And then what is this guy? It's like x to the 6th minus 1 over x squared minus 1. And then, okay. So like, somehow at the beginning, I'm taking things like x to the n minus 1 and I'm factoring them. So cyclotomic polynomials come from saying, okay, I want to understand how this factors. And okay, it's the point is there's a factor of this that has integer coefficients, and it's the polynomial whose roots. So what are the roots of this? Roots of this are nth roots of unity, but there's a polynomial whose roots are the primitive nth roots of unity, just the primitive ones. And it turns out you can show that polynomial has integer coefficients. Like, for example, here, that polynomial is this, and it had integer coefficients. It's not obvious that it has integer coefficients, but it does. Okay? And that's the polynomial we call the primitive, the cyclotomic polynomial. So it has roots are primitive nth roots. Okay? And you can use it to understand factorization problems. So what I'll say is if you solve this problem and you like it and you want some kind of generalization, ask me and I'll tell you some good reading on cyclotomic polynomials. Okay, but I think first you should solve this problem. This problem is easier than cyclotomic polynomials. Okay, so it comes after this. Okay. Okay, does it make sense? Adam, does it address your comment about cyclotomic polynomials?
Yeah, I just thought like that we could use them to prove this.
You can. You absolutely can.
Similar.
Your intuition is right. You absolutely can. But I suggest first you solve this problem and then you ask me about cyclotomic polynomials. Yeah. Okay. All right. So now what? Now I don't have much time, but I do want to do this problem. So okay. Yeah, so we got some examples of transforming roots, right? Like this guy, this the relation between p of x and the quotient, they're like, yeah, so okay, I want to say something about transforming roots. So what it means is I give you a polynomial, it has some roots. Tell me the polynomial that has related roots. So here I have a polynomial, it has roots r1, r2, r3. Tell me the polynomial that has roots 1 over r1, 1 over r2, 1 over r3. Okay.
We can use Vita's formula.
Yeah, so good. So you can use Vieta's formula, and right. So what you can say is, okay, I want the polynomial that has these roots, right? So what does Vieta tell me? Vieta tells me that, okay, I need to figure out 1 over R1 plus 1 over R2 plus 1 over R3. I need to figure out 1 over R1 R2 plus 1 over R1 R3, 1 over R2 R3, and I need to figure out 1 over R1 R2 R3, and then I can figure out the polynomial. And this I can do, right? I can do because it's what? It's like R1 R2 plus R1 R3 plus R2 R3 over R1 R2 R3. Okay, and this Vieta just tells me what this is, right? And similarly for the other guy, for the next guy, what is it? It's R1 plus R2 plus R3 over R1 R2 R3, and Vieta can tell me this. And okay, so this is one approach. This is a good approach, right? You can figure out what the polynomial is like this. So any questions about this approach? This is a very good approach, and I think everyone should understand it. Okay. But now what I'm going to say is there's actually a faster way. There's a faster way to do this. And the way is like this. Let's consider P of 1 over x. Now, okay, P of 1 over x, what is it? It's 1 over x cubed. I'm doing specifically for this polynomial. It's 1 over x cubed plus 2 over x squared minus 1 over x plus 5. Okay, it's not a polynomial. It's not a polynomial, but I know the solutions to P of 1 over x equals 0. Right, the solutions are 1 over R1, 1 over R2, 1 over R3. So it's almost what I want, but it's not a polynomial. So how can I fix it?
Now maybe we can use Lagrange or
You can use Lagrange, but wait, I mean, maybe how you use Lagrange?
Can we just multiply by x cubed?
Yes, that's the thing. So yeah, so there's a trick here, and the trick is just multiply by x cubed. Okay. And then we get what, 5x cubed minus okay, maybe just write it like this. We get 1 plus 2x minus 3x squared plus 5x cubed. Okay. And we know the roots of this will be 1 over R1, 1 over R2, 1 over R3. And it's a polynomial. So it's the one we're looking for. Does it make sense?
Yes.
Okay, so it's somehow it's a trick. And okay, all it is I took the polynomial and I reversed it. I turned it backwards. Okay, so that's a trick. Okay. So great. Let's do a slightly harder problem. I want to look at this problem here. So this was on the warm-up. It was, okay, you have omega is a primitive nth root of unity. And you want to calculate this sum. 1 over 1 plus omega, 1 over 1 plus omega squared, all the way to 1 over 1 plus omega to the n. So any ideas? How can we do this?
Yes. We can add to each term 1 for the term 1 over 1 plus omega to the power of x, we can add 1 over 1 plus omega to the power of n minus x.
Ah, I see. Okay. So you're pairing. You're doing a pairing. This is Gauss's trick, right? You're pairing k and n minus k.
Yeah.
Okay.
And we multiply everything by 2.
Okay, yeah. So there'll be a factor of 2. Okay, but it's okay. So, but let's see what we get. So
we get
yeah,
we get 1.
On the bottom we get 1. Is that right?
I think.
We get 1, don't we? I see. And okay. I think, yeah, we get 1 because oh, that's very clever. Okay, we get 1. I didn't know this worked. And so I guess the answer is what, like n over 2 or something, right?
Yes.
Okay, it's very clever. I didn't know this works. Okay, thank you for showing me this. I didn't know this works. But now let me propose a different problem. Let's propose the problem. So first of all, everyone understands the solution. It's I think it's very nice. I didn't know about the solution. Any questions?
Wouldn't it work for n if n's an odd number?
Oh, so if n is odd, the problem was like one of these terms, right? So one of the terms in the sum is 1 over 0. Okay, like for example, if I take 1 plus omega to the n over 2, you can show omega to the n over 2. Like what is omega? Omega has angle 2 pi over n. So if I take it to the n over 2, I get angle pi, like a negative 1. You see what I'm saying? Let me just draw. So omega is here. It has angle 2 pi over n. If I raise it to the power of n over 2, I'll get here, which has angle pi, and this is just negative 1. Okay, so 1 over 1 plus omega to the n over 2 is equal to 1 over 1 plus negative 1, which is 1 over 0. So it doesn't make sense if n is odd. Or if n is even, it doesn't make sense. Okay, so let me change the problem because I wanted to illustrate a point. So let me make the problem actually 1 over 2 plus omega plus 1 over 2 plus omega squared plus all the way to 1 over 2 plus omega to the n. Now I think the trick does not work, right? Is it, am I right?
Yeah, it does not.
It does not work. But I claim it's still, you can still do it. So the key is, what are these guys? Like omega, omega squared, omega to the n. What are these? These are all exactly. They're all the so omega is the primitive one. This is all the nth roots unity. So we can say these are the roots of x to the n minus 1. So now I want to use Vieta because I have a sum, but Vieta on what? So let me ask something. Can you guys tell me the polynomial that has roots 2 plus omega squared all the way to 2 plus omega to the n?
It's x to the n plus 1.
X to
No,
the n,
minus 3. X to the n minus 3.
like this?
No, 3 minus 3.
Like this. No, but but let's see. No, but somehow that's what will happen, right? So these will no. So what are the roots of this? We should understand this. So what are the roots of x to the n minus 3? They're going to be like this. They're going to be 3
3
to the
times.
1.
Yes. Oh,
You see, there'll be 3 to the 1 over n, 3 to the 1 over n omega, all the way to 3 to the 1 over n omega to the n minus 1. Do you see?
yes.
Oh, so it's x minus 2 to the power of n minus 1.
Yes, that's exactly right. So it's x minus 2 to the power of n minus 1. This is the polynomial whose roots are going to be these. You see? And now we're almost done, right? So okay, I need to take the reciprocal, but we learned how to do that, right? You reverse the polynomial, right? So okay, so let's write it. Okay, I think I need another page, but maybe I have some space here. Okay, so this is x to the. Okay, sorry. Well, actually, we don't even need to do that. We can just do it like this. We can say, okay, if I want to calculate 1 over r1 plus 1 over r2 plus 1 over rn, I can say it's like this. It's the r1, r2, rn minus 1. It's okay, what is it? It's like I put it all over a common denominator. And then what's the numerator? The numerator will be we'll have n terms, and they will be all the groups of n minus one I can make, right? So you guys understand what's on the numerator here?
Yeah.
Yeah.
But like, what is this guy? This is like okay, if my polynomial is cn x to the n plus cn minus 1 x to the n minus 1 plus c1x plus c0. Okay, so the bottom is like c0 over cn times minus 1 to the n, and the top is I think it's c1 over cn, right? Times minus 1 to the n minus 1. Okay. So what is it? It's the whole thing. Okay, I'm running out of space, but hopefully you can see. It's gonna be minus c1 over c0, right? That's the. Do you see? Does it make sense?
Yes.
Okay, so and then what are those
Wouldn't
guys?
wouldn't it
Sorry?
be easier to just would it not be easier to just flip the polynomial like we did
Yeah,
before?
it's the same as flipping the polynomial. You can also flip the polynomial. Like what happens when I flip the polynomial? I take
I just replace x with 1 over x, and I can multiply the whole thing by x to the power of m. Yeah.
okay, yes. So yeah, you can also flip it, and if you flip it, you get something like okay, you get. Let me just think. Okay, I'm not good at doing it in my head, so you can flip it and you'll get the same thing. But just think about what happens when I flip it. I take the sum. So the sum is the n minus one coefficient over the the sum is the n minus one coefficient over the n coefficient. But that's the same as this, yeah. Okay. Okay, so one way or another, you end up with this, and you can calculate what that is. Yeah, what is that guy? That's okay. So the C1 coefficient is I have to do binomial theorem. I have to take n times minus 2 to the power n minus 1. Yes. Okay, divided by the n coefficient, which is just minus 2 to the power of n minus 1, and there's negative out in front. And so this is that's the answer, yeah.
Doesn't this only work like for primes?
Well, doesn't it only work for what?
For primes.
For primes?
Yes.
Mm.
Like
Well,
assuming that the roots of unity give something to the power of n minus 1, doesn't that only work for primes?
assuming that the roots of unity give what? I
Yeah,
don't understand.
they're all so we're saying that w up until wn
That all
are
of these
the
are the
roots of x. Yeah. Shouldn't
I
this
see.
only work only if n is a prime number?
No, because so this is why we need to assume omega is a primitive root of unity. Okay, so you don't need n to be. So for example, let's go back to our picture here. Here was the sixth root of unity, right? So this guy here, the angle is 60 degrees. This is a primitive sixth root of unity. Okay. Now, if I take its powers, what do I get? I get the 60-degree one. The square will be here, 120 degrees. The cube will be here, 180 degrees. Fourth power will be here, 240 degrees, and the fifth power will be here. So actually, I get all of them. Does it make sense?
Yeah, I just didn't notice that it's a primitive root of unity.
Okay, so it's it doesn't actually okay, it doesn't matter. Okay. So any questions about this problem? Okay, it's a nice exercise. Okay, so we're over time, but there is one problem. Oh, wow, there's actually two problems I wanted to go over. Let's do this. Do you guys want to do one more problem, or you guys have some kind of time constraint or something? Because I'm happy to explain one more if people are okay.
I don't know, personally.
Okay. Okay. So let's okay. This one, problem 14, I think is a very nice problem. So I'll give it as homework and then I'll go over it next time. Okay. It's yeah, it's a very nice problem. It's related to roots of unity. If you okay, I mean should be okay, maybe it's a bit of a spoiler, but like okay, I have regular n-gon, right? And I draw all of its points, all of the n points. So these are the n roots of unity. And then the problem is to find, okay, I draw every segment I can draw, all of them. There's n choose 2. And then I multiply the lengths and I ask what's the length, okay? Or what's the product of the lengths? Okay, so I'll leave it as something to think about for homework, and then I'll go over it next time. But this problem I want to cover because I think it's a good Olympiad problem, and it shows something good. So I'll give 5 minutes to think about it. But what is the problem? So you have P and Q have real coefficients, and they satisfy this identity. So the identity is P of x times Q of x plus 1 minus P of x plus 1 times Q of x equals 1. Can you find what P and Q are? So let's maybe take 5 minutes to think about this. So, do you guys want some more time to think? Okay. Yeah, okay. Maybe I'll write one thing down and then maybe I'll give you some more time to think. So I think the first step is kind of okay, it's like tricky. You have to okay. Let me tell you the first step and then we can think a little bit more. So the first step is to you know we use like functional equation techniques, right? So we plug in some other numbers. So we do this. We plug in x plus 1, right? So yeah, we plugged in into this identity, we plugged in x plus 1 and we got this identity. And now this one is a little bit nicer because there's a lot of common terms. So this is here and this is here. So we can subtract and we can factor. Okay. So if we subtract and factor, what does it give us? So we'll get q of x plus 1 and then times p of x plus p of x plus 2. Okay, so that was from this minus this. And then we can do this minus this, and we'll get minus p of x plus 1 times q of x plus 2 plus q of x. Okay, and this is 0. Okay, and maybe it's better to write like this. Okay. Now I want you to think for some time, or think for a little bit, about what we can get from this identity, really. Okay.
I was thinking of another approach. We can say that p of x times q of x plus 1 minus p of x plus 1 times q of x is a polynomial, and it's also the constant function, so we can try to find which polynomials P and Q satisfy that this gives us. So we just have to
So what
find
is
their
the
coefficients and rank.
what is the expression? What is the expression that's constant?
The expression that's given.
Oh, this one, I see. Oh, here.
Yeah, it's
Okay.
it's supposed to be a polynomial.
Yeah.
So we can just try to
Oh, you're saying we should equate
find which
coefficients, right?
values. Yeah, I think we can just prove. We can start by proving that P and Q have the same rank.
They have the same degree. Oh, you're saying they have the same degree.
Degree,
Why?
yes.
And why is that?
Because let's say P is of degree n and Q is of degree m, then we can just calculate the coefficients of x to the power n plus m.
Okay.
And they have to be
the
zero.
subleading. I see. So you're saying the
Yeah,
subleading
and
term.
that will give us that x plus 1 to the power of n equals x plus 1 to the power of m for all x, which means n equals m.
Okay, so you're saying I look
And
at
I
the
think
sub.
we can proceed. I'm not sure about the answer, but if I had to guess, it would probably be p of x and p of x, or p minus p of x.
Okay, so you're saying the answer is like p of x and what?
P of x or p of x and minus p of x. But I'm not sure, it's just a guess.
So you're saying either p and q are the same or they're negatives.
Uh,
Is that
the
is that what
same
you're saying?
wouldn't both work.
Yeah.
Yeah, I'm just guessing that would be the answer.
But I don't understand what the guess is. I don't it's p of x and what?
Yeah, p of x and p of x.
Like they're the same?
Or
I don't know.
and p of x and p and minus p of x.
Okay, so these are the guesses I see. But I mean this one, will not work because you'll get 0, right? And then okay, so this one actually
Oh,
am I
yeah.
understanding correctly? Yeah, so this one will give no
I'm
solutions.
sorry.
No, it's okay. And then
I
this
kinda,
one.
yeah, I kinda messed up.
I think maybe they both give no solution. I don't know. Okay.
But
Okay,
I'm not
but
sure.
it
Maybe
seems no, but it seems like what you're saying is I start with the leading I start at the top. I show they have the same degree. And I start with the leading coefficient and I say they have the same leading coefficient. And then I go to the next coefficient one by one by induction. I show
yeah.
they're like this. I think it works
First,
actually. I mean, I think
but
what'll happen is at the very end, the constant terms may be something you'll find maybe the constant terms don't have to be the same.
okay. I'll try to do it later.
But yeah, I think it's a good idea. I think it works. I didn't work it out, but I think it should work. Yeah, it's a good idea. I think it works. Yeah, because somehow, this identity is so constrained, right? Because you have all these relations between the coefficients. Yeah. Yeah, so maybe, okay, you can, as an exercise, you can do it for homework or something. But let's see. I do want to talk about this approach a little bit. So, okay, we started with this and we derived this identity. I want to explain how this identity actually makes the problem very, very tractable. So let's see, what is it saying? I have two polynomials whose product equals product of two other polynomials. But what's interesting here is, okay, I know Q divides this, but actually you can show P and Q, they shouldn't have any common roots. Because if P and Q have common roots, this cannot be true. You see, so if let's say p of x plus 1 and q of x plus 1, they have common root r. If you plug in r here, you get 0. So it must be that p and q have no common roots. So if this divides this here, but it has no common roots with this, it must divide this. Does it make sense? So when I'm using a lemma, I guess I'm saying, and this lemma is one of the homework problems, but I'm saying if a polynomial p divides q times r, but p and q have no common roots, then p divides r. Okay, and you can see this from, say, the fundamental theorem of algebra. So you just think about factoring everything, right? Okay. Does it make sense? So this, so yeah, maybe, yes.
B and Q both have no roots at all, because we are talking about real coefficients
No,
and real number.
it's not about real coefficients. It's about this identity. It's because of this identity they can't have any common roots. So for example, suppose p of r plus 1 equals 0 and p and q of r plus 1 equals 0. Okay, then this identity doesn't work. You get 0 equals 1. Do you see?
Okay. Yes.
So do you see it really had nothing to do with real coefficients. I could have put complex coefficients here or rational coefficients. It's okay.
So for all x here is x here is a real number.
Ah, that's what you mean. Okay, so let's think. We have an identity that holds for all x. Okay, so maybe it means it holds for all real numbers x. But it's a polynomial identity. If it holds for all real numbers x, it holds for all complex numbers x. Right? Do you see? Because what does it
How?
mean? Because it means this. It means it means p of x times q of x plus 1 minus p of x plus 1 times q of x minus 1 is 0 for all real x. Okay, so
it will have to be
infinitely
0.
many roots. It must be 0, right? You
Yes.
see? Okay, so when we talk about polynomial identities, if I say it's true for all x, for complex x, for real x, for, it doesn't matter. For integer, I can say it's true for integers x, and it's going to be true in general. Does it make sense?
Yeah.
Okay, so yeah, so it's a good point, right? So R here, these R were complex, so I needed to understand that this identity also holds for real for complex numbers. And it does, and so it tells me that the P and Q can't have any common roots. Okay, and so now that I know that P and Q have no common roots, and I have this lemma, which is one of the homework problems, it means that Q of x plus 1 divides Q of x plus 2 plus Q of x. But okay, so let's write that down. It means Q of x plus 1 divides Q of x plus 2 plus Q of x. And now, okay, like this is a very constrained situation. Like these polynomials, they have the same degree. What does it mean which one divides the other? It means they're multiples of each other. Okay, so okay, I won't solve the rest of the problem. I think you should think about it yourself, but it's already a very constrained situation. Like you should understand what this means. Like okay, you should be able to show that, okay, these have the same degree, and the leading coefficient of this one is twice the leading coefficient of this. So it means that this is equal to 2 times this. Okay, and that's from there you can understand more about Q. Okay, does it make sense what I just explained?
Yes.
Okay, so I'll leave it here. I think now you have enough to solve the rest of the problem, and okay, so you can think about it. Yeah, so I think okay, I think it's I'm a little tired myself, so I won't cover this problem, but it'll be, think about it. I'll go over it next time. Any questions before we break? Okay. All right, so let's